So now we're going to do the Lab 7 frequency response simulation. This is the same circuit as Lab 6. We're just going to modify the simulation slightly. It's a two-stage CMOS amplifier with a differential input stage and a common source second stage with RD resistive load. So if you go to your schematic from Lab 6, and we just want to modify our input signal here to be AC amplitude of 1. And we need to add some modeling components here, CGSO and CGDO. And these are given in the lab manual and are also printed right here. And there's no other change of the circuit. VCM can still be 0. The load is still the same as the previous lab. RF is still 1.8K in order to get 4 milliamps, and RD is 2.4K to get the output VO2 close to 0 volts. So now what we want to do for the simulation is do an AC analysis. So we can do a decade sweep. 50 points per decade is sufficient. That just tells you how many different points on the curve you'll have per factor of 10. And then a start and stop frequency of 1 hertz and 1 gigahertz. You can't go down to 0, but you can go like usually multiples of 10 is what is common. So we'll start at 1 hertz, and 1 gigahertz should be high enough frequency where we see everything that we need to in our plots. So click OK and run our simulation. And still upset about me about these NCH inversion parameters. You can get rid of those if you'd like. And I have some old notations on here from the last time I ran this. So I'm just going to delete those real fast. Okay. And it is plotting V load, the output. And you'll see there's 2 plots here. If I get rid of this, you'll see that when I plot V load, I get 2 plots. One is the magnitude and one is the phase. And together these make the Bode plots. And we want to get a bunch of information off of this. The first is, if I click to get the cursors, it'll follow the magnitude plot. I'm not sure how to switch between the magnitude and the phase plots. So we'll just kind of eyeball some measurements. The first thing we want to measure is the low frequency gain. So I move the cursor over to maybe 10 hertz, and we'll get a cursor position there, and that tells us the gain is 40.6 decibels. Next thing we want is the 3 dB frequency, which corresponds to the first pole. So we want to know the frequency when the gain has dropped 3 decibels. So that should be 37.66 dB. So we'll follow this across until we get close to there. And I'm just looking in the bottom right-hand corner to see where the cursor's at. 37.66 is about right there. So we will add cursor position there. And the next point we want is the 0 dB crossing, which is about here, it looks like. Don't need to be super precise, just ballpark it. And that is it from the magnitude response, really. There's some things we want off the phase, but we'll have to eyeball. So I'm going to move this back over here somewhere where it's out of the way. So from this, we want to get for sign off, we want to get a couple pictures. You want to get a schematic picture, so just use snipping tool to get a picture of that, and you want a picture of the Bode plots. So again, snipping tool to get a picture of that. That corresponds to these 2 things. And then we just need to make some measurements based on this plot. So gain at low frequencies is about 40.66 decibels. FP1, that's when the gain drops by 3 dB, and that's the location of the first pole. That's at 37.67 dB, and that frequency is 4.976 megahertz. Unity gain frequency, that's when the gain drops to 0 dB, which is 1 volt per volt. That appears to occur at 319 megahertz. And the last things are phase related. So we need what is the phase at that frequency. So at 319 megahertz, follow this up to the phase plot and then follow that over. And it looks like it's about minus 150 degrees. Minus 150 degrees. So phase at unity, minus 150 degrees. Phase margin is calculated from the difference of 180. So in this case, it would be 180 minus the magnitude of minus 150, which equals 30 degrees. That's about it. 150 gives us 30 degrees of margin. And those are the only things you got to measure for this lab. So once you've done that, you want to upload these pictures and these measurements along with your LT Spice files to the My Courses Dropbox, and you'll be good to go for this lab.